Nuclear power has been a huge source of energy for decades, right? But it's got this legacy, waste that stays dangerous for, well, millennia. Figuring out how to store it safely is one of the biggest challenges in modern science. But what if the answer wasn't some high-tech vault, but a totally revolutionary kind of concrete? So, let's dive into this pretty groundbreaking idea.
So just how big is this problem we're talking about? Let's just look at the raw numbers for a second. Every single year, nuclear plants all over the world create more than 300,000 tons of medium and high-level radioactive waste. That is a huge amount of material that we have to keep completely sealed off from the environment.
Which, of course, leads us to the billion-dollar question. It's not just about digging a hole and dropping it in. It's about making sure that whatever we use to lock it away can handle incredible heat, intense radiation, and just the sheer passage of time. We're talking about thousands and thousands of years.
So why do we call it a forever problem? Well, to really get it, you have to look at the nature of the waste itself. It's not all created equal.
This is where it gets kind of wild. The high-level waste, the really dangerous stuff, makes up a tiny, tiny fraction of the total volume, just about 3%. But get this, that little 3% accounts for a whopping 95% of all the radioactivity. It's incredibly concentrated, which makes it incredibly dangerous.
For the longest time, the go-to solution for dealing with this has been ordinary Portland cement, or OPC. It's basically the stuff we use to build everything. It's cheap, we know how to use it, but here's the catch. When you put it up against the kind of heat and radiation coming off high-level waste, OPC starts to fail. It can crack, it can corrode, it loses its strength, basically creating little escape routes for the very stuff we're trying to contain.
Okay, so if regular cement isn't up to the job, what is? This is where our story gets really interesting. Scientists have been working on a whole new class of materials that might just be the answer: geopolymers. You can think of them as a kind of next-generation, high-performance concrete that's built for the most extreme jobs imaginable.
So what are these things anyway? Well, at a chemical level, it's an inorganic polymer. But the best way to think about it is that as it forms, it creates this incredibly strong and stable 3D network. It's like a molecular cage, and it's just perfect for trapping things inside.
All right, let's put these two head-to-head. Regular cement starts to completely fail somewhere around 600 degrees Celsius. Geopolymers, they can handle a scorching 1,000 degrees and still hold their strength. And check this out, under intense gamma radiation, cement gets weaker, but a geopolymer strength can actually increase. I mean, come on, that's a total game changer.
Okay, that performance is seriously impressive, but how does it actually work? Let's get into the nitty-gritty of how these geopolymers manage to lock away radioactive atoms so darn well.
So the whole idea here is to create something called a waste form. You take your radioactive waste, you mix it with a binder, in this case our geopolymer, and you end up with one solid, super stable block. Basically, the waste isn't just sitting there anymore, it becomes a physical part of this brand new inert material.
And the real magic here is what I'm calling the triple lock system. First, there's physical encapsulation. That molecular cage we talked about, it literally builds a cage around the waste particles. Second, you have chemical bonding. Some of those radioactive atoms actually swap places with atoms in the geopolymer structure, chemically locking them in for good. And third, adsorption. The geopolymer has this huge internal surface area that just acts like a powerful magnet, grabbing onto waste ions and not letting go. It's this combination that makes it so hard for anything to escape.
So with a system like that, you can see why these geopolymers are so versatile. Let's take a look at how they could actually be used to solve some of the absolute toughest problems in nuclear waste.
They're almost tailor-made for handling the really nasty stuff. We're talking about things like corrosive metal scraps from old reactor parts, or contaminated oils, which are a nightmare to deal with. And they're especially good at locking up specific heavy metals like cesium and strontium, which are two of the biggest worries in any nuclear cleanup. And here's a really, really big deal when it comes to safety. When you mix certain metallic wastes with regular cement, the corrosion can actually create hydrogen gas, and you do not want flammable gas building up around nuclear waste. Geopolymers, because of their different chemistry, can lock up those same metals without that dangerous reaction. That makes the whole process a lot safer.
But wait, there's more. The use for these things goes beyond just mixing up waste blocks. For those deep underground storage sites, researchers are looking at using geopolymers to actually line the tunnels instead of traditional steel. A geopolymer liner would be naturally corrosion resistant, which would be a huge upgrade for the whole system's safety.
Now, as amazing as this all sounds, let's pump the brakes a little. Geopolymers aren't some magic bullet, at least not yet. This is still a technology that's very much in development, and it's really important to look at the hurdles researchers are still trying to get over.
And this quote from the research really nails it. I mean, we're not talking about 50 or 100 years. We're talking about keeping this stuff locked up for thousands of years. And while all the short-term tests look fantastic, proving that incredible durability over that kind of timescale, well, that's the main event right there.
So what are the big hurdles they're working on right now? First, unlike cement, the raw materials you use for geopolymers can vary a lot, so getting the recipe right every single time is tough. We just mentioned the huge question of long-term durability. Also, they're great at grabbing positively charged particles, but not so hot with the negatively charged ones. And finally, they tend to shrink a bit more than cement as they dry, which has to be carefully managed so you don't get cracks.
So yeah, there are definitely challenges. But you can't deny the potential here. This stuff offers a kind of toughness and resilience that our current materials just can't touch. It's a fundamental shift in how we think about one of our most difficult long-term problems. The science is still moving forward, but the promise is just immense. So, the big question is, could this really be the forever concrete that finally helps us build a safer nuclear future?